All right, everyone. Good morning. Let's get started. Do you have any questions before we begin? Okay, so uh, so let's see where we were last time. So last time we discussed 8.4, so-called the sample variance, and also under the title of chi-square distribution. So let's review what the results were. So the summary of main results. So we have the following. So first of all, right, the definition of the sample. So maybe let me start out with the context, right? We always have the context that we have a IID sequence. This is our sample, our random sample. So for now, let us not assume the population distribution, but let's just say that they have population mean mu and variance, population variance sigma square. It's very helpful again to remember that these mu and sigma square are unknown. They're constant but unknown. So first is the definition of what the sample variance is. So the sample variance is the spread, right, the average of the spread around the sample, around the sample mean. Okay, so that's their definition. Second is not it's not really one of the main results, but is very helpful decomposition that allows you to think about the sample variance or to work with the sample variance. I find this very helpful, and that is this following decomposition. Okay, so again, it doesn't say much about the sample. I mean, it doesn't say anything about the sampling distribution of the variance, sample variance. But as you recall, a lot of things and can be deduced from this identity. Also, some further properties we will be discussing today will also come from this identity. So again, you should appreciate why this identity is very helpful. It's helpful because right here is your sample variance, right? Divided by n-1, then will be sample variance. The difficulty, all right, of the sample variance comes in two places. First, the square. The square is actually not too bad. I mean, squaring a random variable, it's not that bad to work with the square if you know the distribution of the original random variable. But that is the point, that the original one, okay, is xi minus x bar, or in other words, these xi minus x bar are not independent, right? These are not independent. And summing non-independent random variables are way more challenging than summing independent random variables, if only because of the results like moment-generating function, okay? If random variables are independent, then the moment-generating function of the sum is the product of moment-generating functions, okay? But again, right, because all these summands include the x bar term, they are not independent. So summing them up, looking for their explicit distribution will be a more challenging task. So this identity allows you to decompose, right, the sum or s squared into two components. Each of them are very easily understood, again, in terms of independent property. X bar is well understood, okay? X bar is the sample mean, is very easy to deal with. And of course, X bar being the sum of Xi is the sum of independent random variables. Mu is again is a constant. It doesn't affect the distribution in any dramatic way. Here, right, you subtract mu from Xi, square it. That still preserves the independence among these random variables. So in other words, of course, right, the square here changed the distribution of Xi minus mu, but in terms of the sum, you're still looking at a sum of independent random variables, okay? So this identity accomplished that for us. In other words, analysis of these two components are quite easy because we deal with sum of independent, and if you want, really IID, independent identically distributed random variables, right? X bar is also like that. And so from these two properties, you can deduce back the property of S squared, okay? So then, of course, the first measure, the first important result that we have is that the sample variance is unbiased, okay? Or we haven't introduced that term. You can think of it as on average, your sample variance will be around the true variance, okay? And again, I want to emphasize this result is universal. In other words, this result does not depend on the population distribution assumption. And unfortunately, okay, this is where that this is as much as we can say in terms of universal result that does not assume any further property on the population distribution. For example, we did not discuss this, but you should kind of contemplate a little bit. Why don't we discuss the variance of the sample variance? Okay, and by the way, that's not like kind of repeating myself. The variance of a sample variance is perfectly right, well-defined concept, because by sample variance, we just mean this quantity, which itself is a random variable. So it has, you know, all the moments, including right, the expectation and the variance. So, and the variance here, of course, what we're expecting is a constant, right? A constant answer. And this is not easy because it will require, at least with our current assumption, we don't have enough information. We require the fourth moment, up to the fourth moment of the population, okay? We require up to the fourth moment of the population before we can say something about this. And even if we want to, the calculation will be not that pleasant. So we'll return back to this. But by question mark here, I just mean it's not nice or it's not convenient for us to deal with at this level of the assumption, okay? Part of this course, and if you will, you guys are going toward like a more advanced portion of mathematics from now on in your career, and more advanced math more or less deals with modeling, okay? And so modeling, the most important thing you want to keep in mind about modeling is the assumption. Depends on what kind of assumption you make, you will get different conclusions, all right? The most common mistake students make is they are not aware of what assumptions they are making or they are allowed to make. Sometimes the students make too many assumptions, and of course that's wrong because you're not supposed to assume those kind of assumptions, but sometimes you assume less. You don't assume enough because you are not taking advantage of all the assumptions you can make. So knowing what your rights are, if you will, in terms of legal, right, legal term, make you that much more, I guess, you know, strong in terms of how you can solve the problem. Okay, so here I put a question mark because I cannot answer this question universally. We will answer this question in a particular context of the normal, as you will see soon. So, right, like as I said, now we will specialize, okay, into normal context. So xn, IID, normal, mu, sigma square. Okay, so we make one further assumption on the population distribution. With that said, of course, because these are universal, I mean, only this, right? It still holds, but what we have is a much more in-depth result, right? In this case, we have this universal result, which is super important because we'll keep using it again and again. N minus 1 S squared over sigma squared will have a chi-square N minus 1 distribution. Okay, so that's first. Maybe let me put that as 5, right? Result 5. Where, of course, chi-square itself is an important result, where the working definition of chi-square will be the sum of independent normal square. Okay. So this is the most important result we get out of the normal assumption. All right. And let's see, okay, why this is important. Last time we spent time explaining what this is, and prove why that is true. So today, let's just explore, okay, the implication of this a little bit. First of all, let me emphasize, okay, a very, very common mistake that students make is they make a short, statement out of this, and then it turns out to be wrong. The statement is not that the sample variance has a chi-square N minus 1 distribution. Okay, I know that students make the statement. I myself used to make the statement too, because I don't know, just not being careful, okay, and it becomes a bad habit. But notice it cannot be right in any context, unless I guess you have N equals to 2 and sigma squared equals to 1. Otherwise, right, the sample variance itself is not a chi-square distribution. Well, it's very close to it, right? All these are called the so-called normalizing constants. So again, multiplying and dividing a distribution by a constant doesn't change it much. But on the other hand, right, right is right. In other words, if this is a chi-square, then this cannot be a chi-square. I mean, same distribution, all right? So you must have normalization happening before you can say it's a chi-square, all right? Also notice, right, there's a normalization with the unknown population variance right here. So second of all, okay, what is the implication of something like this? Well, so let's just playing with the chi-square a little bit. By playing, I mean let's ask simple questions about a chi-square. And of course, because if you can say something about a chi-square, automatically you say something about this. Okay, because this is this. So for example, if we have a random variable x that has a chi-square with n degrees of freedom, what are its expectation and variance? Can someone tell me? And the reason why I ask these questions is because they're meant to be answered rather quickly. And they're meant to be answered not with a density calculation. Okay, anything. Okay, very good, Derek. They're both on target. Can you explain why? I guess you could know it, and which is perfectly acceptable to me. But I'm also more curious on the reasoning behind it. Knowing the reasoning can help. Very good. That's fine. You read the book. That's perfect. But I would suggest, right, sometimes just memorizing the fact is fine. Sometimes there's no rhyme or reason, it's calculation. Sometimes there are rhyme and reason, and knowing the rhyme and reason can help memorizing a lot. I claim that here I can perfectly explain everything very easily. So at least the first term, the expectation. Does anyone see why the expectation must be n? All right, so this highlights the importance of the working definition. I am sure, right, after the lecture last time, you are so impressed with the density that all you have in mind right now is what the heck is that crazy density? Like I said, theoretically, we start with the density to establish what we need. but practically, okay, unless we really have reasons to, we don't go back. Here is the working definition, and we will use it as much as we can. In other words, because a chi-square has this representation, well, its expectation will be this expectation of the sum. Okay, but of course, expectation of the sum is a sum of the expectation. Now, can anyone tell me what the expectation of zi square is? What is zi? Okay, and what is expectation of zi square? Correct, right there, exactly from here, right? It's exactly the variance, and you see that exactly the first n that Derek said is very straightforward, just from that. Any question? Okay, so the second one is a little bit less straightforward, but it's just actually involving a fact. And it's actually a fun fact anyway that you should know. So what about the variance then? Well, you should surmise that the variance exactly follow the same route. In other words, the variance will be, and notice what I said here is universally true, besides the fact that I use the zi square, zi being standard normal. Here I need the independence, okay? Here I need the independence between the zi, but I have it, so I can, okay, do this variance inside without a covariance term. All right, now what is variance of zi square? I guess from Derek's answer, you should know, you should be able to guess what it is, right? But why? So first of all, what and why? What is this? What is it supposed to be? And I said, right, Derek is correct. So what should this be? Yep, very good, right? Because it's 2n. Okay, and notice if you like Derek, very good. You look at the appendix to learn more. You figure out 2n, and you notice this relation. You should be able to deduce right away. This must be 2. Mathematics works like that, right? Almost like a detective. Okay, but if this is 2, why is it 2? So how do we work out variance of zi square? What is the formula of variance? Oh, again, right? I mean, a lot of times things just go back to definition, no more than that. It should be expectation of the square, which is the fourth. I think that is minus, right, Madhav? Minus, right? Expectation of the square minus the square of the expectation. No, it's fine. Perfect. Don't worry about it. It's good that you participate. Feel free to make mistake here. Making mistake here, no points off. Making mistakes on exam, right? Lots of points off. So make mistakes here, and then you learn. So all right, we just said, what is this? This is 1. So what should this be? And this is 2. So what should this be? Right, very good, 3. And that is a universal fact that I said you should know. Okay, namely the fourth moment of a standard normal is 3. All right. So there you go, right? Everything can be explained. Now, of course, I guess some of you will come back to me and say, well, yeah, sure, you learn too much statistics. You know that the fourth moment of the normal is 4. Sorry, it's 3. Like, fine, yeah. But again, right, that's a universal fact you should know, because something to do with kurtosis, all right, which is a very important quantity, is to do with fourth moment. But besides that, right, I claim that the fourth moment of normal is very easy to compute. All right. And you're like, what? Okay, so how would you compute the fourth moment of a standard normal? So, right, let's explore that too. And again, my point being here is not showing off to you, impressing you with my knowledge, but to show you that there are always easy ways to do stuff. All right, you just have to kind of look for it. So the fourth moment of a normal, okay? Does anyone know how to calculate that in the least painful way? So let me do the simple-minded way, right? I don't know anything better. Let me just do the density calculation. Okay. Looks fantastic, right? And of course, somehow this is supposed to be 3. Can anyone see why it should be 3? I was expecting someone to say something like that. That is actually a very good traditional answer, all right? Except that if you ever try your hand at it, it's not painful, I think, because it's going to be e to minus t squared over 2. Doing it 4 times is not that bad, I think. Yeah, I would say that's a valid answer. But I think I have a slightly easier way too. And it has to do with integration that I want to show you. Yeah, your answer is perfectly fine, Madhav. But sometimes do notice that people always say you can differentiate moment-generating function to get moments. It's not that pleasant to do in practice, because the fact is, as you keep deriving, the formula gets more and more complicated with chain rule and product rule. So I don't find that process very pleasant, starting at the third and the fourth level. But yeah, your answer is perfectly fine in this case. Let me show you, okay, that a lot of times, this is nothing but calculus skill, really. What you could do in this case is to do it like this. And you see what's going on? This is your perfect U sub. So you do integration by parts, where you integrate this and you differentiate this, right? And because this is a perfect U sub, integrating this gives you e to minus z squared over 2. Differentiating this gives you 3z squared. So even without even like calculation, I know it will come down to something like this. Of course, right? If you really do go bring out the whole integration by parts, you have the the boundary calculation you need to do, but the boundary terms are zeros because of the exponential. Is that okay? You see what integration I did? There's an integration by parts with a U sub implicit, where here this whole thing is like the dv term. For those who like the udv kind of formulation. Okay, but you see what is this? What is this integral? This is the second moment of the normal, which we just say is 1. So that is just 3. And there you go. So I hope that you're convinced that this is slightly easier than the fourth derivative of the moment-generating function. Any question? Okay, all good. So now, right, let's not lose track of what we have. We're playing with the chi-square and what we got, right? So recap. Whoops. Recap is we just said something that you can look into the back of the book, which is, again, very, very good. You should do that. But I would like to encourage you to even go above and beyond. In other words, right, think about the reasoning for the results if you can. Anyway, right, so we got this. And then, right, but the point is, of course, to relate this back to our statistical context. So far, what we've done is purely probabilistic results, right? Exploring things probabilistically. Now, tying it back to our statistic, in other words, we have n minus 1 s squared over sigma squared, right, has a chi-square n minus 1 distribution, okay? So by the way, for those of you who are not familiar with this notation, right, this means has a distribution for sure. What that does is it's like an equality, but the equality is not like a number to a number, but a distribution to a distribution. So what it does is it allows you to say, you know, probabilistic statement that applies to the left-hand side must apply to the left-hand side, right-hand side, left-hand side, right-hand side. For example, if you take expectation here, then you can also take expectation here, and they're equal, right? Variance equal variance. Probability equals to probability. CDF equals to CDF, all right? That kind of thing. So obviously, okay, then we utilize both sides and we say that expectation, okay, of this must be n minus 1. But these being constants, oh, sure. Okay, yeah, do ask questions. So basically, it's just a trick, right? You know, e to my z squared over 2 does not have an antiderivative, right? E to my z squared over 2 does not have an antiderivative. But z e to minus z squared over 2 has an antiderivative because I have a perfect u sub right there, right? That's the observation. So what is the antiderivative of this? Is e to minus z squared over 2 with a minus in front, I suppose, right? So when you glance at this and your mind really is burning for an integration by parts, it does not do you good to differentiate this because you just make things more complicated. You definitely want to differentiate this, but right, again, then you cannot integrate this. So of course, right, the compromise or the way is to reserve a z so that you can make this into a perfect integration or perfect easy integration, and the rest becomes differentiation, right? And so when because you integrate this, you get something like this, and you differentiate this, you got 3z squared, right? All in all, this convert to this because the boundary terms like becomes 0. So, you know, like udv is equal to uv, right, at the boundary minus vdu. And this going here is nothing but me quickly telling you that this is 0, right? Notice the minus and the minus here becomes a plus, and that's that. And you can really trace this back, you know, at home if you want to. And you'll see that what I said is valid. Question? Yeah. All right. So like I said, right, so now we will utilize our knowledge to investigate the expectation and variance of S squared. So here, right, these guys being constants, they factor out. Which of course implies that expectation of S squared is sigma squared. Now, of course, right, I would say nothing new, right? Great stuff, but we already knew this because remember, right, we said we have a universal result that is independent of the normal assumption. We're making this calculation based on the normal assumption. So, of course, right, if the universal result is true, it is just also true when you make more assumption. If you make more assumption and it's not true, if it's not consistent with the universal result, then you're in trouble. meaning you have to go back and see where you make a mistake, right? So this is nothing new, but it's a reassurance that, at least all our derivations seem to make sense. There's no hole in it, okay? But of course, right, there's something new, right? So this is nothing new. In other words, it's just being consistent with the universal result. The new part, of course, is to leverage, right, our extra assumption, which result in this for new information. So of course, the new part, right, is the variance. Because we can take the variance, which, remember, before I said is a question mark. But now we can do it because we know the variance of this. All right. So the variance, these two terms go out. And this, of course, being 2n minus 1. Therefore, variance of s squared is 2 sigma to a fourth over n minus 1. And there, right? This is new. Of course, new, but dependent on the normal assumption. Okay? Be very clear on that. Without a normal assumption, I cannot make this statement. But if I know the normal, after the normal statement, then this automatically comes out. I'm not sure if like this is one question in a textbook for your homework or something, but there it is. Okay. Any question? So compare this, right? Compare this with expectation of x bar equals to mu and variance of x bar equals to sigma square over n. No, Alice, that's what I just said, right? This part right here is not universal because I just did this on the chi-square, right? I used the chi-square result. The chi-square result depends on the normal assumption. So the moment I move to a different distribution, no, it's fine. Definitely ask questions, right? The moment I move away from the normal distribution assumption, I lose this result. I lose this result. But I still have this, right? I still have this. Okay. So, all right. So this is the result for the sample mean, and this is universal. Okay. So you see how easy the sample mean is. For the sample mean, you easily derive expectation and variance, not assuming distribution of the population. While with the sample variance, right, you need, so this part is still universal, but this part requires normal assumption. But side by side, do appreciate their structure, right? Their structure actually tells you the same statistical message, okay? Statistical message. What message? Yeah, thank you. I'm so into the moment, I forgot. Yep. Yeah, right. The statistical message, right, is what? These guys, remember, what are their roles? We haven't really got to the formal idea yet, but they're supposed to be the stand-in, right, the estimator for their unknown, right, population counterpart, mu and sigma squared. So these are the observed, and these are the known value. And so on average, your sample mean is on target. On average, your sample variance on target. What else? When the larger the sample size, the more precise these estimators are. That's exactly this message, okay? And that's exactly, it tells you the advantage, right, of having a large sample. In other words, the error, right, these are the error you make. These are the error you make for your estimation because, right, it's how far away from the target you are on average. The error you make is proportional, right, inversely proportional sample size. In both cases, right? Forget the -1, right? When n is large, -1 doesn't change anything. So there you go. Okay. So also you could, if you want to be more precise even, this will allow you to decide, okay, the sample size so that you have coverage rate, meaning the probability that the true mean and the true variance is inside that. We'll talk about confidence interval, right? It'll allow you to decide with some kind of length, right, of the confidence interval, what kind of sample size you require to achieve some desirable coverage rate. Again, we'll talk about that later. But again, like all these, okay, tied together to give you statistical information that you can use, okay, to construct your intelligible report on the unknown population parameters. But they are very similar in structure, is what I want to say. Any question? All right. So I know I have said this, right? But let's make it more explicit. And what about non-normal? Okay, I mean, you should have this kind of questions in your mind, whether they can be answered or not. So, right, so for example, let's say you have x1 up to xn, IID uniform 0, 1. No, right? Of course, if you 0, 1, then we have nothing to say. But, again, maybe 0, 1, AB, for example. Okay. So, of course, you can still form the sample variance, all right? Sample variance is a universal concept that applies to anything. Right? So you should ask this question, can we still say expectation of S squared, right, is equal to, well, in this case, going to be sigma squared, which is B minus A squared over 12, right? Variance of S squared, I don't know, is 2, whatever that thing is, right? So this is sigma squared, sigma to a fourth over n minus 1, and then, right, n minus 1, S squared over sigma squared has a chi-square n minus 1 distribution. Can we still say all of this glorious stuff for our normal sample? Can we? Yes and no, right? Yes and no. Yes here, no here, and no here. All right. So then, of course, right, there's still a question of, so these are negative answers, right? No, no, yes. But if no, then what can you say? All right. So can we say something, right? About S squared, right? In this uniform sample. By about S squared, I mean about the distribution. Okay. Well, then this answer is iffy, all right? I mean, of course, you can never really prove a negative. In other words, I cannot say no definitively if there's nothing here. So I would say not really if n is small. In other words, by not really, I mean, it's not anything. I can do this, all right? This is valid. Under this assumption, it's still a random variable. It's still valid for me to ask what distribution it has. I'm not saying it's impossible. If you give me the whole day, I'll be able to answer something for you. But A is not fun. B is not appreciated. because it's not some name distribution. It's not some well-known distribution that people care about. Okay, so that not really, again, is that kind of message. I can work on it. I can give you some answers. You're like, okay, looks cool, but right, it's not among the categories of things that people, keep in their library and remember, right? Of course, because there are too many things, right? Exponentials, Poisson. If you classify everything, then you have no room to store anything. But notice what I say if n is small. All right. So far, so far, right? The message I'm trying to give you is this. In modeling, or at least in statistics, right? There's this kind of assumption about population distribution, and it usually gets divided into two camps. If it's normal, you can say something, and if it's non-normal, you can say less, but maybe something. All right, so you should pay attention to that. There's another division in terms of the treatment of the theory. That is, if n is small, sample size, assumption about sample size. Again, these are assumptions, all right? Meaning may or may not hold. You have to see what situation you're in. If sample size is small, you can say something. If sample size is large, you can say something. Okay, and when for small sample size, the results are what we would say are exact, meaning it is what it is. There's no error. When n is large, the result, as we will say, is asymptotic. In other words, is approximation. Okay, and so you should be aware of at any time where in these four categories you're in. Okay, like for example, before I was discussing normal and small sample. By the way, when if it's true for small sample, of course it's true for large sample too, because it's exact. The converse does not hold, right? Whatever you say for large sample may not hold for small sample, okay? Because it's approximation. So before, what I was discussing is normal and any sample size, small or large. Also, I was discussing right here, non-normal and small sample. Now I will move to non-normal and large sample size. Now, I want to remark, right, that asymptotic is not something this class focuses on, all right? For different reasons. A is a more advanced topic. You need more, calculus analysis tool to make your statements precise. And B, yeah, maybe that. And B, there are many things to say about this anyway. That's a focus. But that doesn't mean that you should not be aware of this, and I would keep telling you these kind of statements. The book does too, right? But kind of superficially. And that's that, because we just tell you the results without explaining it. And the reason, right, is because when you go to more advanced classes or when you read standard treatment of statistics, it's usually the asymptotic distribution they keep referring to. Why? Because it simplifies things. It allows them to make statements in a universal way. All right. So you should pay extra attention to this in terms of results, in terms of what they're trying to tell you. But I claim no explanation. Okay. I claim some explanation, but not like deep explanation. All right. So what asymptotic can we talk about in this case for sample variance? So first, right, let's actually go back and talk about a fun fact about chi-square. So asymptotic for chi-square. Okay, and I think your homework, right, has a lot to do with this. From your homework, I think a big part of the claim from the text is that chi-square n, right, as n goes to infinity. And by the way, right, as n goes to infinity is another way to say it's n large. I sometimes don't like this statement so much because it seems to be misleading, because you think infinity, you think a billion. In real life, right? A professor of mine, when I was doing graduate work, usually asks how large is infinity? Is it 10? Is it 30? Right? Infinity or large depends on whatever context it is. And in statistics, as I said, sometimes large or infinity starts at 30, meaning your conversion starts to look good when the sample size is about 30 or so. It's just a mysterious number people quote. I like to start at 100 or so, but it depends. Anyway, right? When n goes to infinity, the chi-square distribution will be approximately, right, or converge to a normal distribution. Okay. And of course, with what kind of mean and what kind of variance, and why. And again, right, this is your homework for this week, so you may or may not have started thinking about this already. But yeah, so 3 questions. What are the mean and the variance of this normal that the chi-square is supposed to converge to? And why? Don't be too quick, Derek, right? 0, 1 is the standard result that we keep saying for central limit theorem. But that's because things are normalized. And a lot of statements you read may or may not be normalized. So again, right, that's why math is a little bit difficult. You want to pay attention to the statement. I'm not normalizing anything here. So no, it's not 0, 1. Let me save you the suspense. It's 2n and 2n. You're talking about the Z transformation, Christine. Yes, after you figure out the mean and the variance, then you can do that. Yes, but right now I'm asking exactly what the mean and variance are. Okay, so right, of course it's still n and 2n. Shouldn't surprise you because that's always the mean and variance of chi-square. Okay, so again, I think students tend to kind of, I don't know, neglect this fundamental piece that things is what it is, right? Just because you approximate with a different distribution doesn't mean you change the mean and the variance. Okay, so this is still true. And of course, that means, right, from what Christine said, and by the way, you should divide by the square root of the variance, all right? So what this says, right, is that the textbook may give you some kind of version like this. And that's exactly what Derek and Christine might have in mind when they think of this. But I urge you, right, to see that this and this are the same thing. That's exactly the skill you should have when you do statistics. This and this are the same thing. This is just a normalized version of this, the scale version, right, and location, centralized version of this. I claim that this is much easier for me to write down. This is kind of like twisting my way backward, right? Because I know what the mean and variance of chi-square is. Once I write this down, I can just transition to this, okay? Because the message, the importance is about the normal. It's not about the mean and variance, really, okay? Does this make sense? I think the textbook asks you to prove something like this. So there you go, except for the reason, right? What's the reason? Yeah, but you are reinventing the wheel. Because remember, this is approximation. This is not exact. If it's exact, then sure, MGF is lurking around behind the background, right? Like your quiz one. This is approximation. So NGF is the tool anyway, but you are working very hard to reinvent something. And that something is central limit theorem. Okay. Whenever you see some kind of normal convergence, do think central limit theorem, because as far as I'm aware, that's the only result that leads to this kind of thing. And also, of course, right, when you think of this, central limit theorem, by the way, right, is about the sum of independent random variables become approximately normal. That's a message, all right? That's just a message. The sum of IID random variable become approximately normal. Do we have any IID sum happening for us? The answer is yes, we do. Right there in the working definition. So it's exactly in the setup of the chi-square. It's in the nature of the chi-square to be close to the normal when n is large, right there in this definition. Okay. So this might confuse you because you're like, then why invent the chi-square? Isn't everything normal? You know, like my elementary teacher tells me, I don't know, high school, whatever, right? When you take elementary statistics, everything is normal, right? So why waste your time and my time, right, lecturing about chi-square when everything is normal? Anyone? Well, again, right, the reason is do not be fooled by the result, okay? Do not be fooled by the flashy result. You have to see when the result holds. It only holds when n is large, all right? And a lot of things in life does not happen with large sample size. So therefore, right, the normal is cool when you have large sample. In fact, right, if we can sample infinitely often or whatever in life, right, you think of COVID-19, if they have like infinitely many patients that they can test a vaccine on, I'm pretty sure they can get a very reliable vaccine by now. The whole point is, right, you never really have access to large sample size, ethical reason, I don't know, money, whatever, right? So small sample results are super important in a lot of cases, right? So sure, right, again, this works is approximately normal when it's large. When it's small, it's not close at all, and it's very different. Chi-square and normal are very different at a small level of n. And so therefore, right, you cannot confuse the two. And therefore, right, you must learn the chi-square to use it precisely for the small sample. Okay? Any question? All right, so that's asymptotic for chi-square. What message does this say? The message, it says, of course, it's about chi-square itself, but also the message is if you have IID normal mu sigma square, right? So you have normal population. Then the sample variance will be approximately normally distributed with some mean and some variance, okay? I don't care to specify. I can calculate it, but I'll leave it when n is large. Actually, you know what this is, right? This is the same mean and same variance I calculate for the sample variance under a normal assumption. Okay, why do I know this? Because the n-1 s square over sigma square has a chi-square distribution, and chi-square is approximately normal. So therefore, s square is approximately normal when n is large. Okay, that's for the normal population. Okay, but you're like, this is a redundant result because I already know, right? S square for any n. I know the exact result. I know chi-square. This is cool, but I don't need it. That's correct. Where do you need something like this? You need something like this when you don't have normal assumption. Non-normal. So for example, let's say uniform AB. Okay. Then you can still form the sample variance, okay? Like I said before, you can still have the sample variance. And like I said, it does not have chi-square, right? So n minus 1 s squared over sigma squared does not have chi-square distribution because it's not normal. So here, if you want to say something easy, then you must use asymptotic. In other words, in this case, when n is large, it is true that the sample variance, in this case, is approximately normal, okay, with some mean and some variance. So that's the message, that for the non-normal population, the sample variance is also approximately normal when n is large. But there's a catch. The catch is this normal is not related to the normal coming from the chi-square. All right. This normal is not related to the normal coming from the chi-square. And finally, all right, where does this result come from? Where does this result come from where s squared is approximately normal? Because certainly it doesn't come from the chi-square, okay? It doesn't come from the chi-square. Because, like I said, for non-normal population, you do not have chi-square distribution. The answer is it comes from its own structure. It comes from its own structure. What structure is it? The structure of the identity that we just talked about. The identity was sum xi minus mu square is sum xi minus x bar square plus x bar, and x bar minus mu square. Okay. So notice that, I just noticed that, okay. I think I noticed some difficulty here. So when n is large, this being the sum of IID random variable is approximately normal. This is independent of any population assumption. I want to say that this is also normal because this x bar being the sum is normal, but I have the square outside, so that turns into a chi-square, so I have to see what's going on here. Okay, I think my what I say here is not correct. So I will not explain this. I'll just say that for when n is large, the sample variance for non-normal population also is approximately normal. But I will just leave that as an observation. When I find a better explanation, I'll tell you. Okay, so the message is this, that for non-normal population, unfortunately, you cannot say anything about the sampling distribution of the variance. You can say something about asymptotic, meaning when n is large, it's approximately normal. But again, right, these are more like FYI for your information. We don't use that. We don't use this so much in our class in terms of exercise, homework, kind of exam question, that kind of thing. But I do think you should be aware of this because, not everything in life is about normal distribution. Okay. Any question about these things? All right, so let me show you, all right? I think all these talks are more convincing when you see something with your eyes. So let me show you the simulation again, right? So you see how it works in, hold on, let me see. All right, can you see the screen here from my code?
Yes.
Okay, thank you. All right, so this, all right, is the normal population. So this is the classical result. I have normal assumption, okay? This is under a normal assumption. So here, what I want to show you is the different, the chi-square approximation that is true for any sample size. So what I do, right, is again, like I said, I fix sample size. Here, sample size is 3, okay? Sample size is 3. And I keep resampling with sample size 3 to get my sample variance. And when I plot the histogram of this, which is the, I don't know, I'm a little bit colorblind, so I think this is blue or something, you know, pardon if I use the wrong word, blue or something. The blue thing, right, is a histogram. And then, of course, I plot the curve, okay, the density curve of the chi-square distribution. And if the approximation result is correct, this should be close for any n. All right, this is n equals to 3. Let's run it. Notice the chi-square shape looks like this, right? Let's say n equals to 10, sample size 10. Notice, right, the chi-square shape changed. And notice how it looks a little bit more normal. Okay, but notice how the histogram and the density always closely fit. I don't know, n equals to 5. See, change shape, right? Appreciate the density shape change, but the histogram always follow the density, all right? And then let's go to infinity, all right? Let's go to infinity. Let's go to infinity at 30. See how it looks more normal, right? Again, right? We are under the normal assumption here, normal population. So this says two things, right? The sample variance becomes normal distributed, and also the chi-square become normal distributed, okay? Chi-square with here 29 degrees of freedom, right? Let me change it to 100. See? And I'll be more convincing, all right, when I show something else, the normal curve. Notice this, I don't know, orange, green, whatever line, is still the chi-square density, all right? I'm not plotting the normal density here. I'm plotting the chi-square density, all right? So before I show you the normal stuff, all right? So this is, when n is about 100, this is what I think of as asymptotic, okay? When n is equal to 3, again, this is what I mean by exact result, right? This is not normal. Anyone who put a normal thing on this is just saying something nonsense. And that's why you need to learn the chi-square when n is small, okay? And even when n is large, it's good to know that it's exact. Any question here? So let me move to the sample variance. Can you see this? I switched to the screen, right? It's fine. This is for the uniform. It's okay, right? You see the uniform one.
Yes, we're good.
Okay, appreciate it. All right, so first let me show you, right, when n equals to 3. You see how, right, the chi-square curve, which is like the same curve as before, and the histogram don't fit. All right, why? Because the uniform sample variance does not have normal distribution, does not have chi-square distribution, right? Let's push it to a little bit different. Nowhere does it fit. Notice something interesting though, right? The sample variance itself start to take normal shape. Like I said, the chi-square also start to take normal shape. But these are two separate facts, right? I mean, same fact really. Central limit theorem is behind them both. What I mean is like, but they are not on the same scale, right? And even when you push n to 100, right, which is we say when n goes to infinity, right? Both are pretty normal, right? Except They don't fit. So again, right, this reinforced my message about non-normal population does not have chi-square distribution. But you see, this is a separate statement from the fact of saying both of them tend to some kind of normal when n goes to infinity. Any question here? Now, finally, right, let me show you that the normal approximation holds good. So here, right, I will do a normal curve. So I will plot like a normal density curve, all right, the normal density curve. So this is a silly graph, right? Because when n is small, or maybe not too silly, actually, maybe it's good. When n is small, right, notice the normal assumption does not hold, right? This is normal, this is chi-square, nothing like each other. Let's push n to 10. Better, right? But still, notice the chi-square is the exact. Normal still doesn't hold, okay? But let me go to infinity now. See how the two curves are very close to each other now? Right? So this demonstrates, right, three things. Chi-square, right, the sample variance of a normal population is still chi-square. The chi-square itself goes to normal. The sample variance goes to normal. And the normal curve, right, is there to verify that. They do both go to normal. Okay? Any question here? So I superimpose a normal curve on this to reinforce the idea that yes, right, the curve is normal. It's not just looks normal, it is normal because I do the normal density. Okay. So now, like same thing, right? I will superimpose the normal density on the plot. There, you see this tightly snug curve. This is the normal density using, by the way, what do I do? I do the normal density using the sample the sample average of the sample variance, if you understand what that means, okay? Because I run the sample variance, I get a bunch of variance numbers, right? So I do the sample average of that and the sample variance of the sample variance, all right? But if I run that, it fits snugly, all right? This is a normal curve. Notice the chi-square curve still does not fit. Again, why? Because the sample variance of the uniform or any non-normal distribution does not have chi-square distribution. Of course, the chi-square itself goes to its own normal right here, right? Pretty good. But that's not the normal of the sample variance. Any question? All right, so this program, of course, is shared to you on Canvas. I don't know if I did it as detailed as this, but of course, those of you who know how to program, you can just do the same thing as I did here on the code. The basic codes are there for you to play with if you want. All right. Any question? I hope I demonstrate the ideas to you on this distribution. All right, so enough of that then. Let's move on, right, to with our theoretical lecture. So next stop, we will skip 8.5 and 8.6 for now. The reason for this is they discuss the T and the F distribution. Of course, I mean, if you are anywhere near statistics, you know that these are very, very important distributions. But the reason why I don't skip for now is because I think the theme where they belong is for confidence intervals and test that, which comes later. All right. I mean, if I discuss them now, it's just going to be more like a theoretical discussion on probability without the statistical motivation. All right. So I want to introduce the statistical motivation, and then when we do these topics, and then we go back and grab the theoretical tools that we need to work out what we need. So that means we will start the next one at 8.7, order statistics. All right. So order statistics. So let's explain what they are. So we always, right, our context is always that we have an IID sample from whatever population distribution we want. The idea, okay, is that, okay, I guess first of all, right, names that you might hear: sample min, not sample mean, right? Sample min, sample max, median, and even sample quantile, okay, is the names that are associated with sample statistics. How so? Well, the idea, right, is that these are unordered, right, numbers, unranked, right? They just come as they come, right? The first number, the second number, the last number, right? If you were to order, right, these numbers or rank them, then, so of course, right, from smallest to largest, okay? That's always the assumption. Then you got x1, x2, up to xn, okay? So pay attention to my notation. There is a parenthesis behind the around, right, the thing. When you see this, you automatically think order statistics, okay? Or just think of them as the, like, so this is the first element in the ranked list, right? And this is a ranked list. This is the first element of the ranked list, and this is the last element of the ranked list. Namely, right, I hope it's clear then that this guy is the min, and this guy is the max. All right, so that's just notation. Is it clear? Now, of course, right, x1 and x1 are very different, right? Maybe once in a while, they take on the same value. In other words, the first value you see happens to be the smallest. But I would say, right, that happens 1 over n factorial times or something. It's not that often, all right? Same, right? So do distinguish these two, these things. So the textbook, okay, your textbook, I guess, realize this confusion, like to use the notation y1, y2, up to yn for order stats. And you see the motivation, all right, why? I will stick with this my notation. And normally I would try to stay as close to the book as I can, right, to not confuse you. But here I insist on using my own notation, not my own, really, because actually, I think the universal notation for all the statistics is these notations, okay, from all the texts that I've seen and I learned. Calling it y actually is a bit unusual. Okay, so I will use this. You can feel free to use whichever you want, as long as you clearly state their order statistics and you use your notation consistently, then I understand what you're doing, all right? But my notation will be this, okay? And again, right, do not confuse them with this. Any question? All right, so of course, for example, right, so in the ranked list, the middle element somewhere, right, the middle element, so if n is odd, let's say when n is equal to, let's say 5, right? Then the middle element, right, is the median, right? If n is even, I guess you learned that rule. You add the two, if n is even, right? Let's say n equals to 4. Then you sum up, right, the two middle value, and you divide by 2 is the sample median, right? Anyway, I mean, there are ways to figure out, right, what we mean by these things. And the sample quantiles is the same way, meaning like, what's the point in the sample that's 90% of the sample fall below, right? So I don't know, let's say the 90% quantile. And you see, actually, these are, right, a little bit awkward stuff because there's some rounding involved. If you have perfect sample, meaning 10, perfect number, then of course the ninth one, right, is the 90% quantile, right? Meaning 90% of the sample is below it, 10% is above it. But when n is not 10, right, then it's still some kind of average like this, right, to get to 90% quantile. But the rule, at least for me, is unclear. I don't look into this stuff too much. The point being, though, right, we're not caring so much about the, we do care about the median, all right? But we don't care about like how to really define the quantile and everything like that in this class. The point being, though, is that they all derived from the order statistics, all right? They all derived from the order statistics. So the philosophy is if you understand the order statistics well, then all the things like the quantiles, the median, you can also understand. All right, of course, I mean, at least in theory. So our goal, okay, is to derive the sampling distributions of the samples of the order statistics. Okay, and that's the goal of this section. In particular, actually, we will only assume continuous distribution here, continuous population distribution. We don't talk discrete for technical reasons, as I'll explain. So when we assume the population distribution has a density, we will derive the density of all the order stats. We will have an abstract result for the density of the order stats. Okay, that's the goal. That's the goal of this section. Now, so that's the more like the theoretical result that you must know, and you will use it at some place. But what is the practical side of things, right? What is the use of order stats? Now, I think, right, I mean, I don't have to convince you that order stats is very popular. I give you your exam, right? You definitely would want to know what the max is, what the min is, right? I don't know, just maybe to comfort yourself. Also, you want to know the median, right? Maybe you're consciously, unconsciously not aware of this, but you're asking for order stats, right? You are asking for order stats from the sample, right, of the random midterm scores that you receive, that we create, right, from the exam. So that's clear, right? That somehow you just want, given a sample, you just want to know the max, the min, and the median, and all the things. But even in a more theoretical framework, suppose you have x1 up to xn IID coming from a uniform family. Well, of course, right, A, B are assumed unknown. Or in general, any bounded family, all right? Notice we have worked with unbounded families a lot, like the normal or the exponential. There's no bound on them, right? There's no limited interval where they live. Here is a bounded, right, distribution. So when you look at a sample, right, you now definitely want to know what's A and what's B. These are unknown. So naturally, the sample max is a natural estimator for B. The sample min is a natural estimator for A. And that's the statistical context that we'll be working with a lot. In other words, right, you want to understand B, or you want to say something intelligent about B, you better say something about the sample max. Same goes for A. All right. So I realize time is up, so we will continue with the order stat on Friday. Okay. Thank you. You too. Thank you. No, so solution to homework will not be posted. If you want any particular question answered, you can send me an email. I'll write down the solution and I'll post it for the class. But don't request too many, right? Request something that you really want to know, and I'll write down the answer for that. I'll post it. I either share with you or I'll post it on the canvas. Okay, but not all solutions. Yep, just request some particular questions and I'll answer for you. All right, have a good day.